Dos.
Muy buenas tardes a todos. Gracias por atender nuestra invitación nuevamente. Damos inicio hoy a la tercera conferencia dentro del ciclo de conferencias geodinámica del doctor Peter Molnar, y él nos va a hablar en el día de hoy sobre energía potencial gravitacional. Thank you, Pete. Thanks.
Hector.
Okay, go ahead.
Okay, thank you, Hector. So today I'm going to talk maybe at greater length than you want on gravitational potential energy per unit area and how it bears on large-scale dynamics of mountain building. And I should say the concept of available gravitational potential energy goes back a long time to Lorentz, a meteorologist, atmospheric scientist, the founder of chaos, incidentally, who described this for the atmosphere. And the key is this is the potential energy per unit area that's actually capable of doing work. One can have lots of potential energy that's of no use whatsoever. So what's important is this can do work. And I would argue if isostasy is the most fundamental concept of crustal dynamics and mountain building, gravitational potential energy per unit area is the second most fundamental concept. So I will indulge you for quite a bit. So just going back to isostasy, area isostasy, one has a crust where the crust is thickened, it stands high, but the column of mass down to a depth of compensation is the same everywhere. This is the basic idea. And in Pratt isostasy, as we understand it today, the same is the case, but instead of crust being thickened, one has a hot upper mantle. So the differences here is difference in temperature and thermal expansion of the hotter material relative to the cooler material. But there is a depth of compensation where they become the same, and this is important. So to remind you, the potential energy is just the integral of the force times displacement, which we can write this way. But if we go to the simplest case, a mass at a height z above the ground, the force is just mass times acceleration, g is gravity, and the potential energy is the integral of mg over height. And of course, if you go from 0 to some elevated surface, it's just mgc, z is the height. The implicit idea here is that the potential energy when you're at z equals 0 is 0. This is just the definition for this case. So this is stating this. You have a mass at some height, h. The potential energy is the mass times gravity times the height, mgh. If we consider a column of mass in here, where we have this red is a column of mass, it's got a density rho, it stands a height h, the same h as over here, cross-sectional area delta A, the mass is simply the density times the volume, the height times the cross-sectional area. The pressure at the bottom is simply the mass per unit area, the height of the column times the density times gravity. And the potential energy is the mass, that's the density times the height times the cross-sectional area, times gravity, times the mean height. Just take the average of heights in here. And that's h over 2. So the potential energy is a half density, gravity, height squared, that squared is the key in all of this, times the cross-sectional area. But what we care really is potential energy per unit area. So if we divide that area out, it's a half rho g h squared. Again, the squared is what's important. Now, if we look at this in a different way, let's let this red area be a fluid, and we calculate the force per unit length, and per length coming out of the screen, coming towards you or going away from you. The force per unit length that the fluid in here, this red fluid, applies to the walls of the fluid is the average pressure times the height. Well, the average pressure is a half rho gh. The pressure at the bottom, rho gh, the pressure at the top is 0. So it's a half, and then it's times the height, h, it's a half rho gh squared. Per unit length as the potential energy per unit area. They're the same in this case. Again, assuming we let the surface be the definition of 0 potential energy. So this is the important point. Force per unit area, force per unit length, sorry, and potential energy per unit area are both proportional to the square of the height. And I'm going to beat on this very hard, but this means that for mountain ranges and high plateaus, they should reach a limiting height, because eventually they'll become so high you can't push them any higher. But just to back up, the key point, the difference in potential energy per unit area, which you measure in joules per meter squared, is the same as the force per unit length, which you measure in newtons per meter. These units and these units are the same. Joule is a newton meter. So it's the same as the force per unit length that one column applies to another. And this is telling you the units are the same. This concept is crucial. We talk about potential energy per unit area, but what we care about in building mountains is the force per unit length. So just to emphasize this, suppose you double the height of this region. So the pressure at the bottom, in this case, rho GH, pressure becomes 2 rho GH. But the potential energy, the potential energy then is the mass times gravity times the mean height again. It's this same formula that we have over here, half times rho GH squared, half becoming, because the mean height is a half. If we compare that in this case, pressure at the bottom is twice as large, no surprise. But the potential energy, the mass is twice as large because you have twice as high a column. So it's twice, the mass is twice as high, but the mean height is also twice as high, h. So you wind up that the potential energy per unit area is not a half rho GH squared, but is 2 rho GH squared. You double the height, you quadruple the force per unit length and the potential energy per unit area. So once again, mountain ranges and high plateaus should reach a limiting height. Eventually, you will not have the force per unit length you need to lift the mountain range any higher. It will just reach a limit because of this. Now you can say, well, this is just a column of mass above some level. This isn't the Earth's crust. And I will then go through the same argument later, thinking about that. But just to emphasize this once more, this has twice as much mass as this. If we put that same twice as much mass at the same elevation, so we double the cross-sectional area, then the pressure at the bottom is the same. The potential energy over the whole region is greater. It's twice as large as this case because it's twice as wide. But the potential energy per unit area stays the same. So you can widen the mountain range without gaining as much potential energy as you do when you elevate the mountain range higher. Here, going from here to here, you double the potential energy. Going from here to here, you quadruple. Again, an argument that mountain ranges should reach a limiting height and then grow wider. You'll see this again. I will beat this down harder, I'm afraid. So gravitational potential energy is, if we then go into a continuum, the gravitational potential energy in the Earth, if we take sigma ZZ as the lithostatic pressure, the weight per unit area, potential energy is that force per unit area integrated over depth, dz, from the surface, from the depth of compensation to the surface. So you can write this separately. The vertical normal stress, the lithostatic pressure, is simply the integral from some depth to the Earth's surface of the density of the rock times gravity times this height coordinate in here. This is the same as what we went through just a minute ago, but in the form of calculus. So the potential energy above sea level, sigma, would be the lithostatic pressure. The lithostatic pressure is simply rho gz. You integrate that and you get one half rho gh squared when you go up to the surface. The same as I showed you with those red blobs of fluid between vertical containers. So let's compare the situation between a high range up where this is a high plateau or a mountain range. Its height is delta H, and it's got a crustal root down here of big delta H down here. The depth of compensation is at the bottom at this area. And let the depth of compensation be the reference level where Z equals 0. So here, in what I'm going to address, Z equals 0 is down at this point, and Z will increase upward in the case that I consider here. And I've changed slides, so I'm worried that I may have made a mistake, but that's what I'm going to assume. So for terrain with density of rho c, c for crust, standing little delta H above the surface, and with 0 potential energy per unit area at z equals 0, which is the depth of compensation, and is at a depth below the surface of H plus, that should be a delta H. I failed to change that to Greek. And where H is the normal crustal thickness, and here it is, delta H is excess depth, we simply have this integral. We integrate the density of crust times gravity times depth over depth from the bottom, the depth of compensation, to the top, which is through crust of this thickness, little delta H, H plus big delta H, and you get this same formula that you've seen, quantity squared. Another way of looking at this is to make a plot. Lithostatic pressure on this axis, depth going down. On this axis, at this bottom point in here, the lithostatic pressure is simply the density of crust times gravity times the thickness of the crust above. This entire thickness, where delta H is the thickness of the root of the crust, H is the thickness of normal crust, little delta H is the crust above. And so this is the same formula that I just wrote. You integrate that and you get this equation here. And I point out the slope of lithostatic pressure increasing with depth is simply crustal density times gravity, rho Cg. It's a straight line, constant crustal, assumed here, constant density of crust, gravity is constant, and you get to this point down here. I point out that the potential energy is the area, this is an integral, so it's the area in the shaded region, which you could look at it as a triangle. It's obviously a triangle. This shaded region of pale gray is a triangle, and the area is a half times the height times the width. Well, the height is the sum of all of these, the little delta H, H delta H, little delta H, H plus big delta H, and the bottom, the size of the bottom is the lithostatic pressure, which is this product. Well, if you multiply this times this height difference over here, you get this formula right here. I show you this because let's compare this with terrain with no height. So here, the top of the Earth's surface at sea level is the top of the rock in the crust. It has normal crustal thickness coming down to here. And then its mantle down region. So the slope of the red line is crustal density. The slope of the black line here is crustal density times gravity. Down here, it's a steeper slope because it's mantle density. And at the bottom, the mass per unit area is the same. So the lithostatic pressure is the same, but there's a difference in area between these two. First, what's the area below this curve, this one that comes down in this region shown above where the moho is, above the depth of compensation? Well, you can look at it as three regions, a triangle here, triangle, a half times crustal thickness squared, rho GCG, a half, a rectangular or square area, rectangular strictly, over here, where it's simply crustal density times gravity times the height, times the thickness of the crust, because this product is the lithostatic pressure at that depth, and this height difference. And then another triangular area where here it's mantle density. So one has this product, half rho G, rho M, mantle density times delta H squared. So this region is a sum of these three terms, which you can get obviously if you integrate that and just keep track of all of the terms. So what's the difference in potential energy per unit area? This is the concept that's important. It's this difference that we care about. It's this difference that Lorentz referred to as the potential energy that can do work. Most of the potential energy I've just mentioned is useless. It does us nothing. And the potential energy difference between the two is the potential energy that's equal to the force per unit length. And so this difference, this little shaded area in here, again, you can look at it as three triangles, a small triangle of little delta H height, just a small area, a half because it's a triangle, rho GC delta H would be the lithostatic pressure at sea level below this region times its thickness, delta H. This trapezoidal shape. It's not a rectangle, but again, same logic. The lithostatic pressure difference at the top is simply the weight of the rock up here, and you multiply that by a thickness h, so you get this term, and then another triangle where one takes into account in the mantle, although I haven't made that clear because it's buried in here with this delta H. The mantle is involved in this. So this sum, if you add these up, the half, you have a delta H in front, you have a half here of this, you have a full H, and then a half of big delta H over on that side. So the difference in potential energy per unit area between this region and this, the high regions and the crustal root and the low neighboring regions, is this quantity right here. And remember, this is the same as a force per unit length. And I've made these slides at different times, and so this H in here is H0 down in this case. This is H0. So sorry for this confusion. It's a lot of work for me to change the equations, it turns out. Well, if we assume area isostasy, so area isostasy merely means that the mass above sea level, rho c times the height in here, this has to be compensated by a deficit of mass, which is the difference in density between the mantle density and the crustal density over the thickness of the crustal root down in here. If we use this and we put this formula into this equation, we can get this, where basically we've multiplied through by delta H squared over 2. We've multiplied by delta H in here to get this term, rho CG delta H, big H. But then we've substituted for delta H here with this into this term and into this expression. And so we wind up with this delta H squared, big delta H squared. Now you may wonder why I'm doing this, and this will become clear in a second, because I'm going to undo this in just a second as well. But the question to ask here is, what's the rate of change of gravitational potential energy per unit time, the rate of change in the difference in the gravitational potential energy between the high region and the low region? And the answer is, if you differentiate this, of course, the derivative of that with respect to time is going to be 2 delta H, derivative of delta H with respect to time. So the 2's cancel out. There's the derivative of the rate of change of the height. You do the same with this term and you get that. Well, when you do that with this term, again, you get rid of the 2 and then you substitute this back in and you wind up with this equation. And we could linger on this. I don't want to waste time on this, but I think it's obvious that it's not complicated to get from this down to here. And why is that important? Well, this says that the rate of change of the potential energy over time is simply the product of the density of the crust times gravity times the crustal thickness itself times the change of height of the surface above. So as you raise the surface, you increase the potential energy per unit area of that elevated region, and hence you increase the difference between the elevated region and the neighboring lowlands. So the rate of change of gravitational potential energy is proportional to the crustal thickness, that factor, and to the rate of change of surface height, that factor right there. Let's back up a little bit. To build a mountain range or a high plateau, you have to do work against dissipative processes, friction or viscous dissipation, and against gravity. If you didn't have friction or viscous processes, of course, if you built a high range, it would just flow away and disappear. It wouldn't last. It needs some strength to remain, and it resists deformation as you build that region. But there are two resistances, these dissipative processes and gravity. And work done against gravity creates potential energy and increases nonlinearly with height. This is nonlinear. You have delta H squared here, and because big delta H is proportional to little delta H, again, you have a squared term. Again, this is emphasizing that it's easier to widen a mountain range than build one. So suppose we have crust. This orange is crust of thickness h, in this case h0 and one of those other plots. You displace it, you raise a high plateau to a height delta h over a width w, and you create a crustal root down in here. The difference in potential energy per unit length, now here length is in and out of the screen, toward you or away from you. And the difference is between the high region and the lower region. That's the difference that we're talking about. That's the same formula that I gave you before, multiplied by the width of the range, the W up in here. Now let's suppose we widen the range. So we displace this another increment so that we now have a range that's twice as wide, same height, same thickness of crustal root. Well, the gravitational potential energy per unit length coming in and out of the screen is twice this. It's twice as wide, multiply W by 2. And so all of these terms get multiplied by 2, and you have this formula. Compare that with raising the mountain range to twice its height. Instead of delta H, as we had here, it's now 2 delta H. And you thicken the crust so that the root is twice as thick. Big delta H here, big delta H, now 2 big delta H. The gravitational potential energy per unit length stored in this region compared to the low region now is the same as one would get if one doubled delta, little delta H and doubled big delta H. Well, when you do that, you get this formula, which is not the same as that. I think you can see that if you multiply that term by 2 and you multiply that term by 2, you wind up with sorry, and you've got to multiply that term by 2 also because you've doubled that. You wind up with a factor of 2 in front and you get rid of these halves that are in here. So if you take the difference in the potential energy per unit length coming out of the screen here, in the case where you've doubled the height versus the case where you've doubled the width, so we subtract this equation from this equation. W2 delta H is this one. 2W small delta H is this one. Subtract those two and you wind up with this amount. There is more potential energy per unit area, per unit length coming out of the screen stored in this case than in this case, even though you've shortened the crust the same amount. So this is not going as the quadruple of the doubling of height, but it's still going non-linearly with increasing the height. The difference in potential energy between doubling the crustal thickness and doubling the width of the plateau is such that more work, more force per unit length has been needed to double the height than to double the width. And so mountain ranges, again, should reach a limiting height and then grow wider. Eventually, it becomes too difficult to lift the mountain higher, but one can still make the mountain range wider using the same force per unit length. I think I beat that hard. So Tibet is a good example. This is the Tibetan Plateau, and it's high, almost 5,000 meters, and it's wide. It's 1,000 kilometers across the north-south. Here it's 2,000 kilometers east-west. It's very flat, and we look at this as the pressure gauge of Asia. This reached a limiting height, and instead of growing higher, it grows wider with time. This is what we think. I'm not going to show you evidence of that, certainly not today, but this is what we think. So we see it as the pressure gradient. Okay, I want to go a step in a somewhat different direction, but a little further by looking at the equation of equilibrium. And I'll simplify this if this looks difficult. But the key here is that there are gradients in stresses. So this is a stress tensor. The delta operator is effectively a gradient. It's a divergence operator, but this makes gradients, is equal to the body force. The body force is the density of a parcel of rock times gravity. It points, in this case, it's going to be downward. We're going to let Z be downward from now on. But this is a force due to gravity. It's acting on a body and we have stresses, and you presumably know about stresses. So force induces a stress. If you have a body force to keep this from accelerating, Newton's second law, you'd have acceleration, you need to balance that with stresses, with gradients in stress, but the stresses effectively keep this from accelerating and going away. But then you have stresses that you've created to do this. These stresses can do work, they can move density anomalies. And so there's a balance here. This is an equilibrium state, but it doesn't necessarily stay the same forever. You can get movement because of stress. You can move the body force, change the body force by changing the density anomalies in places. But the important point is that this is not a statement of cause and effect. You can't say that the body force is responsible or the stresses are responsible. They're always in a balance. And that's often, I think, poorly appreciated. So if we take this is a vector equation, and we write all three components. So sigma xx, this is the x component of compressive stress, and the gradient of that in the x direction would be how the horizontal compressive stress oriented in the xx direction, how that would vary with the x direction. Sigma xy is the shear stress on vertical planes associated with strike-slip type deformation. Z is pointing downward. And so how that varies in the y direction. So if the x direction is across the screen, the y direction would be into the screen. Whoops, didn't mean to do that. And then this is balanced by then the shear stress xz. You can think of this as a stress on a horizontal plane induced by the above and below moving with respect to one another or undergoing forces with respect to one another in the x direction. And there's the gradient in the z direction. This because there's no body force, this is zero. That's the first of the three equations. This is a vector equation. The second, same thing with y. The y component of compressive stress, the gradient in the y direction, is balanced by a perpendicular component gradient of the shear stress that's associated with strike-slip deformation, and the vertical component of the stress on the horizontal plane, or could be a vertical plane, but due to vertical movement, that's going to be zero. And then the third of these equations with the z component, well, this is the same, this equation is the same, but now we were worrying about the normal stress in the z direction, and that's equal to the body force, rho times g. I'm going to simplify all of this further in order to make a couple of points. First, let's just make it, it's two-dimensional, x and z. We throw out the y dependence, so we get rid of all three of these terms. That's it. So we wind up with these three equations, two terms in each of the first two terms balancing the body force in this one. And let's make it even simpler. Let's say there's no y dependence. So this is purely a two-dimensional case in xz with no variation in the y direction. So we can just throw these terms out, and we wind up with just two equations. So think of this as two equations applying to a mountain range that is linear and goes from plus infinity to minus infinity. No variation along it. So we're ignoring y components of stress. Okay. Now, to solve these equations, we need boundary conditions. Let's assume there's no shear or normal stress on the top. This is effectively saying that the wind causes no tectonic deformation. I don't think any of you would doubt this. The wind or streams, there's no shear stress on the top. And there's no normal stress. The weight of the atmosphere doesn't matter. And we make the same assumption on the bottom. This is a more restrictive assumption, but still sensible. There's no traction from flow in the asthenosphere on the bottom. So we're just looking at a layer with no shear stress, no normal stress on the top, and a layer at the bottom, again, that is free of tractions. Okay, so we're in a situation, this is what I want to consider here, where we have lowlands, thin crust. This is the lithosphere crust mantle. Can compare that with a high region. Topography is exaggerated with a crustal root. And these are our two simple equations, no y dependence and just simple balance here. And let's start with this equation. Let's integrate this equation, the horizontal gradient of the horizontal compressive stress plus the vertical gradient in the shear stress on, call them horizontal planes, integrate this over depth. Well, if we integrate this over depth, integrate that, d sigma xz dz, integrated over depth, the answer is simple. It's simply the value of sigma xz at the top minus the value of sigma xz at the bottom. This is calculus at its simplest. But we've assumed that that's zero. There are no winds, and we assume no tractions at the bottom, so that goes to zero. Remember, we assume no tractions at top and bottom. So if we then integrate the first term, integrate that term over depth, so this is the horizontal gradient, sigma xx, oriented in the x direction, integrated over depth. Well, this we can say is simply the lithospheric thickness, because we're integrating from the bottom of the lithosphere to the top of the lithosphere, times the average horizontal compressive stress in here. That's all this is, and we're saying its horizontal gradient is zero. Integrating over depth, we simply get the product of the average value of this times the layer thickness. This, for those of you who studied calculus, this is called the mean value theorem in calculus. Now, this is actually a rather profound statement, because what this says is that this quantity, if its horizontal derivative, its horizontal gradient is zero, it means it's constant. This quantity, thickness of lithosphere times the average horizontal compressive stress, is constant independent of x, independent of the horizontal position. So if we look in a situation like this, what that just said is the force per unit length integrated over this depth is the same as the force per unit length integrated over this, and that force per unit length is the product of the thickness of the lithosphere times the average horizontal compressive stress, the horizontal compressive stress that is tending to shorten this region or to extend it. It's not clear which it will be, but it could be either one. This is constant, and because the lithospheric thickness is approximately constant, remember, the topography is exaggerated in this case. So the thickness of lithosphere under this region and the thickness of lithosphere under this region are almost the same. They're within 1% or 2% of each other. They're not different enough to matter. So if L is the thickness of the lithosphere and it's approximately constant, then the average horizontal compressive stress is also constant. If this quantity is constant and L is constant, well, then sigma, the average of sigma xx is constant. And so, insofar as the assumptions made so far are reasonable, and they're pretty serious or strict assumptions, but insofar as they're reasonable, variations in tectonic style do not depend on lateral variations in the horizontal compressive stress. The horizontal compressive stress does not vary, so there are no horizontal variations. Instead, it must vary, it must depend on lateral variations in the vertical compressive stress, which owes its difference to differences in crustal thickness, and therefore on elevation and how isostasy is sustained. So let's take this a little bit further with one even simpler assumption. We've made these assumptions: no shear or normal stress on the top, no shear stress on the bottom, no traction from flow of the asthenosphere. Still simpler assumption: negligible shear stresses on horizontal or vertical planes. And this is what underlies Airy isostasy. This is what Airy assumed. I don't think if you read Airy's paper, you'll see that he assumed this, but this is essentially what he was assuming. And so what I want to do is take you back. And did I state the assumption? I'm negligible shear stresses on horizontal or vertical planes. So if we take that second equation, what we're saying is that this quantity is zero. The first term vanishes. There's no shear stress on vertical or horizontal planes. So this just goes away. And hence this equation, this top equation, reduces simply to the vertical gradient in the normal stress is equal to rho g. Well, this is what we assumed already. This is the vertical gradient. This is the vertical gradient in lithostatic pressure, simply rho times gravity. And if we integrate that, we wind up with the lithostatic pressure. The vertical normal stress is simply rho g times z, the thickness of the layer. We had this before, but we know this, right? And this varies. In this region, you have crust above sea level, not here. So the vertical normal stress, the lithostatic pressure, will be higher beneath the mountain range all the way to the bottom until you get to the depth of compensation down in here. So throughout this part of the region, throughout the crust to the depth of compensation, you would have the vertical normal stress possibly, I'm not going to say definitely, but possibly larger than the vertical normal stress over here. Or sorry, the vertical normal stress is greater in this area than it is over here because of that greater height. So sigma zz is larger beneath high regions than beneath low regions. This is inescapable because air has a much smaller density than rock. And beneath high regions, therefore, sigma zz can be, not necessarily, but can be greater than sigma xx, which would favor normal faulting there. Beneath lower regions, where sigma zz may be the smaller than sigma xx, for a constant value of sigma xx, we might find sigma xx greater than sigma zz, and hence thrust faulting is likely on the flanks. But I insist that what I've told you does not guarantee this. Neither normal faulting in high areas nor thrust faulting in low areas is required. And the reason is we don't know what sigma x is. This constant allows that constant to be whatever the world has given us, or for whatever reason nature has provided a horizontal compressive stress. It can be big, it can be small. But you can easily imagine beneath the plateau, sigma zz will be greater than that horizontal compressive stress. And you can easily imagine that beneath the lowlands, the horizontal compressive stress will be greater than the vertical normal stress, average stresses through this column. And so you can imagine normal faulting would be favored in this region and thrust faulting would be favored over here. Again, I insist, if this quantity is big enough, you'll have thrust faulting here and here. And if this quantity is small enough, you'll have normal faulting here and normal faulting here. You can't solve this question. But you can look at a place where you get an answer. And I take you back to the Cordillera Blanca in Peru, and you have underthrusting of the Nazca Plate on the west side. Here's the Pacific Ocean. You have underthrusting of the Brazilian Shield on the east side, thrust faulting on both flanks, but normal faulting in the middle in here. And so what that is saying is we have this situation. The vertical normal stress beneath the Cordillera Blanca is greater than the horizontal compressive stress, but beneath the flanks, it's the opposite. The horizontal compressive stress is greater than the vertical normal stress. And hence, one could actually put a bound on this quantity right here, because this quantity has to be larger than whatever one gets with isostasy here, and smaller than whatever gets with isostasy in this region. So I want to go through a couple of misunderstandings that pervade the literature, and I should say these are misunderstandings that I have made. If you go read old papers I've written, you'll find I've made many of these mistakes that I'm going to mention here. But transmission of stress. If we go back to the basic equation of equilibrium, gradients and stresses are balanced by the body force, the gravitational body force. The point here is that transmission of stress is a non-concept. Gradients in stress and body forces must balance, and stress must be transmitted You can't stop stress from being transmitted. You can't just suddenly have a wall that says, well, there's no stress on that side of the wall. So stresses have to be transmitted. That's inescapable. A regional stress field. Remember that this, from the simple arithmetic, we got this to be constant. It's not regionally varying. This is the constant. The horizontal normal stresses are subjected to the equations of equilibrium, but the regional variations need not be large. This can vary. This has to vary over space, but for different reasons from which I've told you. The point is, this doesn't likely vary a large amount. What varies is the vertical normal stress. And we often confuse stress and deviatoric stress. Structural geologists often get these confused. Stress is the sum of the pressure, P is pressure, and the deviatoric stress. The deviatoric stress is stress without the pressure. So stress is the stress tensor, and here I've been using it as positive if compressive, but that's not necessarily, that's an arbitrary choice on my part. The pressure is the sum of the three principal components of stress, sigma 1, sigma 2, sigma 3, divided by 3. It's just the average of those. This is the Kronecker delta. If I and j are equal to 1, sorry, if I and j are equal, then this quantity is equal to 1. If I and j are different from one another, this is 0. And this is merely saying that if you have pressure and you're looking at a compressive stress, pressure is part of that compressive stress. And also there is this deviatoric stress tensor that's in this. If you have shear, just shear stresses, then pressure doesn't matter. This goes away, and the deviatoric shear stress and the shear stress itself are the same. They're not different from one another. The reason that this is important is the stresses do work. It's the stresses that build the mountain ranges, but it's the deviatoric stresses that cause deformation, because pressure causes negligible deformation. Pressure is important in fluid flow. It varies from place to place. It's not something that can be ignored, but pressure does not deform rock significantly. The rock is effectively incompressible. So deviatoric stress is what causes the deformation. But if you want to worry about the work that's been done, you have to include the pressure as well, because the pressure contributes to the work. And so a bunch of what I would call deceptive or useless slogans: over-thickened crust. Well, what's the reference frame? Over-thickened with respect to what? It's merely thickened. When I read over-thickened, I think the people who've written the words don't understand. Orogenic collapse. Of course, high terrain can extend because it's got more potential energy per unit area than the lowlands. But you can also have a region extend if the margins are pulled apart. This is a slogan that belies a misunderstanding of what is built mountain ranges and how they might be destroyed. Gravity-driven normal faulting. Normal faulting, in nearly all cases, extracts gravitational potential energy, and therefore all normal faulting, and I put nearly because you can contrive exceptions, is gravity-driven. This gravity-driven normal faulting is just extra words to say the same thing. Okay, I want to take this, I've forgotten where I'm going now, but rate of change of potential energy per unit area. Remember, this is the potential energy per unit area difference between the high terrain and the low terrain. It's the area in this red curve where we've plotted lithospheric pressure on the horizontal and depth going down in the vertical in here. And if we put numbers in, remember I gave you this formula, and I gave you this formula. If you take the rate at which gravitational potential energy changes with time, it's simply rho g times the crustal thickness times the rate at which the height changes with time. So the rate of change of gravitational potential energy is proportional to crustal thickness and to the rate of change of surface height. I said this once before. So for energy, surface uplift is what matters, not rock uplift. If the surface goes up, the rock goes up. But if the rock goes up and erosion is removing rock, the surface may not be going up. In the energy balance, what's important is surface uplift, not rock uplift. much confusion surrounds rock uplift. So this is a list of these useless or deceptive slogans: overthickened crust, orogenic collapse, gravity-driven normal faulting, and rock uplift. Work is needed for surface uplift. Isostatic balance can cause rock to go up. If you erode, remove material, isostatic balance will make the remaining rock rise relative to sea level. So let's just put some numbers in. If we say the density of crust is 2.8 times 10 to the third kilograms per meter cubed, gravity 9.8 meters per second squared, then for a crustal thickness of 35 or 70 kilometers, normal thickness, thick crust under a high mountain range or plateau, and let's use a rate of surface uplift that's very fast, 1 millimeter per year, not outrageously fast. There are places where one has this. That's the value in seconds. The rate of change of potential energy per unit area is 300 or 600 milliwatts per square meter. That's just multiplying these numbers together. And the difference between these two is simply that the crustal thickness is greater when you get to 70 kilometers. To raise it 1 millimeter a year is twice as hard as raising it when it's 35 kilometers. I remind you, the average heat flux from the Earth is 60 milliwatts per square meter. 1/10 of this, 1/5 of that. And so the point is, only a very efficient engine could power surface uplift at 1 millimeter per year, which is the same as 1 kilometer per million years. This is very fast, and it takes a very efficient engine to make that work. And moreover, as crust thickens, more energy is needed to raise the surface, because this value is for 300, that value is for 70 kilometers. Sorry, this value 300 is for 35 kilometer thick crustal thickness. 600 is for a 70 kilometer crustal thickness. Okay, I want to go back to, again, and now look at Pratt Isostasy, because this matters as well. So here we have crust ordinary thickness, but it's hot under the high area, cold under the surrounding area. Again, the force per unit length, or the gravitational potential energy, is the area of this red curve between these two values, between the value you'd get if you integrated through this column and the value you'd get if you integrated through that column. So it's this area. But what I want to consider is what happens if you remove mantle lithosphere. So if you start with it being cold, but remove some of that mantle lithosphere and replace it with hot material, what's the difference? What do you get? The surface will go up because you've replaced cold material with hot material, but what's the change in potential energy per unit area or in the force per unit length? And so let's just take a simple difference between them. Let's suppose the surface rises because you've removed mantle lithosphere by delta H here, change symbols. So the potential energy, the lithostatic pressure increases going down with a slope equal to the crustal density times gravity. And then at the MOHO has come up, of course, because the surface has gone up. You haven't changed crustal thickness. And then if you come down on this curve, this would be the cold version, the hot version, where you've replaced the mantle lithosphere with warmer material. So this would have a slope of the density of the asthenosphere, whereas the original case, before you elevated, you would come down that slope to the initial MOHO, and then the slope would change, becoming the density of the mantle lithosphere in this area. And the potential energy per unit area is the area in between in these two cases. And you can see it consists of a parallelogram, something with a height delta H and a width. Actually, it's better seen as, well, anyhow, let's not worry about it. It will be rectangular, so it's rho delta H times the crustal density times the thickness of the crust. Again, I've changed symbols. Plus this triangular area, which is the mantle density times, this in fact should be the density difference, not the mantle density. It should be delta rho m in here, times the thickness of lithosphere, and it's a half because it's a triangular region in this case. So let's suppose we remove mantle lithosphere hotter than some amount. Let's suppose we remove the mantle lithosphere that's warmer than 600 degrees or 400 degrees, either case, from the bottom. At the bottom, the temperature is the same. So in a sense, we're taking away some material down in here that's started off as being at some temperature, and we're replacing this with the temperature of the asthenosphere. Well, the average change in temperature is half of what we removed here, because we remove at that level, but there's no change in temperature at the bottom. Again, it's the area of a triangle. And the height change is proportional to the thickness of the layer. And again, I've changed symbols in here. This is now the thickness of the mantle lithosphere. And so the height is simply the difference in densities divided by the background density times that thickness. And that difference in densities is simply the density of the material times the coefficient of thermal expansion. Alpha is the coefficient of thermal expansion times the temperature difference. So it's just this simple number. If you change by an average temperature of some amount, multiply by the coefficient of thermal expansion times the thickness of the layer gets longer by this amount, delta H. And because it's isostasy, the surface then must go up. So suppose we did this, how thick must the mantle lithosphere be for delta H to be 1 kilometer? We put 1 kilometer in here. We're letting delta T be equal to either 300 degrees Celsius or 200 degrees Celsius. Well, when we put the numbers in for a coefficient of thermal expansion, common value for the mantle, 3 times 10 to the minus 5 per degree C, then the mantle lithosphere would have to be either 110 kilometers or 167 kilometers for the different temperature changes, for the different amounts of mantle removed. So first is removal of mantle lithosphere can increase elevations by 1 kilometer. These numbers are reasonable, but not by 5 kilometers. You're not going to get a 5 kilometer surface uplift by removing mantle lithosphere. Now let's look at the potential energy per unit area change, again with numbers. I gave you this formula before. As I said before, this is the wrong value. This should be a delta rho in here. If you have 1 kilometer of uplift and you put the various numbers in, then if you have mantle lithosphere 110 kilometers thick, you get these numbers, 2.7 times 10 to the 12th newtons per meter. I suspect most of you don't know, you don't think in terms of these numbers. Don't worry, I'll get to that. Or you get a bit more if you have the thicker crust in here, because if you make crust 70 kilometers instead of 35, this term is bigger, and that accounts for the difference here. And if you go to the 167 kilometer case, where you remove 20, where the 200 degrees C difference, then in that case, the numbers are a little bit bigger, but they're all in the same range of 3 or 4 times 10 to the 12th newtons per meter. I mention this because the gravitational potential energy difference between a mid-ocean ridge and old oceanic lithosphere, this is what is commonly called ridge push. The force per unit length that pushes lithospheric plates apart at the mid-ocean ridge is the same. It's 4 times 10 to the 12th, the same magnitude. And what this means is that elevating a high plateau 1 kilometer by removing mantle lithosphere resists convergence as much as the mid-ocean ridges push plates apart. This is not a small amount. This is an amount comparable to the forces per unit length that drive plates around the world. So, in summary, this is my last slide. In summary, differences in gravitational potential energy equal forces per unit length that regions apply to one another. These forces per unit length are, if you like, the forces per unit length along a mountain range that build a mountain range, or when they become too small, that allow a mountain range to fall apart. So we can measure gravitational potential energy easily. We simply make it equal to this force per unit length, and we've learned something. The gravitational potential energy increases nonlinearly with height. This is fundamental. This is obvious in the case where one considers material above sea level only, those first red slides that I showed you. But this is the case when one does isostasy properly. And this means that high regions should reach limiting mean elevations. In simple terms, as you increase the force per unit length, or if you have a force per unit length raising a mountain range, eventually that mountain range will become high enough that it equals that force per unit length. The force per unit length can continue to move material towards one another to build a mountain range, but it doesn't raise the height. It simply raises the width just increases the width of the range. The mountain ranges should reach limiting mean elevations, and then they grow wider. They don't grow higher, they would grow wider. Of course, other processes can change, and so one can undergo changes during this process. But in the simple case, mountain ranges reach limiting elevations. Removal of mantle lithosphere can increase gravitational potential energy per unit area more than crustal thickening in regions of the same height. And this is because the thickness of, or the depth of compensation is greater where you've removed mantle lithosphere than where you've thickened crust. And so you have a greater thickness in there, and that enters into the equations to give you even more gravitational potential energy. I remind you, stress does work. Deviatoric stress deforms rock. And then these slogans that I discourage you from using, like transmission of stress, which, as I said, I have used, regional stress field, which I have used, overthickened crust, which I have not used, orogenic collapse, which we all understand, but is a misleading slogan, gravity-driven normal faulting, all normal faulting is gravity drilling, and rock uplift. Of course, rock goes up, but in the energy balance, it's the surface that's much more important, the surface uplift that matters. And Hector, I have actually finished with a couple of minutes to spare, according to my clock.
Thank you very much. We do have one question so far. How do you select the density of a heterogeneous rock mass?
Oh, yes. Obviously, all of what I've done is ignored that. And for what I'm talking about here, it doesn't really matter whether one uses 2.8 grams per cubic centimeter or 2.67 is commonly used. These will change numbers a little bit, but the physics isn't going to be very different. However, there's no question that there are major lateral variations in density of the crust. We know that in Canada and in the Lake Superior region of the United States, the crustal thickness is 50 kilometers, whereas we know further south it's only 35, and yet they're the same height. So there has to be a big difference in crustal density. Big, not big, but in that range of tenths of a gram per cc. So I don't do it. I'm trying to stay with simple physics, but indeed there are differences that are measurable and can be important in some situations.
Okay. There are no more questions, but I would like to know maybe a good explanation from you about this topic related to the intercordillera, thinking in the thickness, that elevation change, what is the boundary of the eastern side of the intercordillera. What is your opinion about this?
Yes, I think I understand your question. I think, first of all, I think that the work that Andres Mora and I'm drawing a blank. He has a colleague. He now works in Brazil, Francisco Parra, I think. I think the work that they've done is very good, and they've shown active, very young deformation, active thrust faulting, beautiful reflection profiles showing the eastern margin of the eastern Cordillera is active and growing. I think, however, what they're looking at is an expansion of the width of the eastern Cordillera. So what they see does not apply to the entire Cordillera. It's the outward growth of the Cordillera. An active outward growth, probably at a few millimeters a year on the margin there. As you know well, the rate of contraction across the eastern Cordillera, 3.7 millimeters a year, plus or minus 1. Probably most of that shortening is there in the region on the eastern edge of the eastern Cordillera. But as I said, That's not telling you about the height of the Eastern Cordillera. It's telling you about the southeastward growth, the widening of the mountain range. And I think it's easy to interpret all of this work. It's beautiful work. I think what Andres Mora has done is excellent. But I don't think one can use it to generalize about the rest of the Eastern Cordillera. Is that did I answer the question you were asking, or did I answer a different question?
No, yeah, that's okay. Thank you, Pete.
Yeah.
Well, there are no more questions, Pete, so far.
Oh, okay. Let's see if I know how to. I'm trying to see you if I can.
Okay.
I can't. I'm not able to. Okay, I'll just get rid of this. Oh, there you are. Now I see you.
Okay.
So when everybody else leaves, I'd like a quick conversation with you.
Yes. Ok, damos por terminada entonces la tercera sesión en el día de hoy. Muchas gracias por su participación y nos veremos el próximo martes a las 4 de la tarde. Tengan muy buena tarde. Gracias.